All right, so I think we should get started, given the tight timing. So my name is Heather Miller. I'm the chair of this session. And right, so our first talk is by Jamie Willis, and it's about Garnishing Parsec with Parsley.
Hi, so I'm Jamie, and I'm indeed here to talk about Garnishing Parsec with Parsley. If you don't know what Parsec is, it's a Parsec combinator library for Haskell, and Parsley essentially is an implementation in Scala that shares the same interface but dramatically different internals that lends itself to become quite fast from JVM. So we're going to start by looking at a grammar and seeing how that translates, and from there we're going to work out actually what is happening and why is it so fast. So let's start with our simple grammar, and we're going to go for expressions. These are really nice, simple expressions. You can add things, multiply things, or use brackets. And I'll note that as it stands, this is quite inefficient, because if we read a factor and can't read a plus, we have to then read a factor again. So let's change it to be more like this. We read a factor and optionally read a plus and another expression, and similarly for factor. And to be a bit more interesting, instead of just building your usual AST over this thing, I'm going to take a function that, when it consumes a map from variables to their values, will produce a parser that can actually evaluate the expressions that it reads. So let's start by translating the num clause of the grammar, which the plus will translate into a function called sum, which says read one or more of the things inside, i.e. digit. And then I'm going to use a map to turn that list of characters into a string and convert that to an integer. Similarly for atoms, I'm going to need to take my parts and OR them together. The angle brackets with the bar corresponds to the OR. And here, these operators say that expr is quite important. They're pointing at it. So a bracket will be read on either side, but they'll be forgotten about. They're not part of the computation that we're actually interested in. Factor is, again, using these same combinators. It's saying, let's take a multiplication function and map it over an atom, and then apply that to a factor. Essentially, it's taking the binary operation and applying it to both things, and making sure that we can read a multiply in the middle. And if that fails, we'll read an atom. As I said, this isn't the most efficient thing in the world, so we will actually take this and turn it on its head. We'll say we'll read an atom, and then we'll do this thing that will return us a function, and we'll apply that to the atom. So we flip the arguments of multiply around. So we apply the y first, and then give it the x. So the type of this operator, just to make it clear, is you give it a parser that returns an A, and an A to B, and it will give you a B. So here's our grammar again, and this is what it becomes when it's converted. It's still quite close to the grammar, but it has quite a lot of stuff around to actually perform conversions and actually do the computation we're interested in. I should note there is a better form for this, which is to use an operator called chain. And chain just says, I have a bunch of things that I want to combine in a linear fashion. And happily it allows us to use curried operators instead of the uncurried ones from before. So how fast does this compare to actually Haskell's version? Or rather, a normal parser combinator library will do this by actually evaluating these combinators. And Parsec, for instance, uses continuation parsing style to do this. I don't. I treat every combinator as an abstract syntax tree node, and I'll compile it to a very small instruction set that is really specialized for parsing, but works with a very imperative core. So I'll take this example, and I'll run it with the original version using the function application, the chain, which is in dark blue, handwritten recursive descent with pattern matching, and I also wrote a reference implementation with the Scala parser combinators library that used to be part of the standard. And we can see that in all cases, my blue lines are further left of the green lines, and they perform quite close to the handwritten equivalents. This benchmark is a bit odd because the grammar is so small. As you get bigger, the actual time differences become much larger. For instance, in the paper, we can see actually that for this specific example, Parsec from Haskell is about 13 times slower than Parsley is for that same example. So we're compiling combinators. What does that mean? So we'll start off with the simplest of the combinators, the applicative combinators. So when we see a PF applied to a PX, we're just going to have the bodies of PF and PX followed by an application. And a pure corresponds to a push, where we're pushing something onto the stack. So all our computation in terms of the applicative operators happens on one of the stacks. The intermediates are pushed on, apply will take two things off the stack and put them together, and push will just put a pure value onto the stack. For these operators, they will, as before, they will do the P and the Q in the order, but they will insert a pop in the relevant place to forget about one of those things. So do P, pop it off the stack and return Q's result, or do them both and pop off Q's. The actual choice combinator is a bit funny because in Parsec, at least, which we're modeling, you will try P, and only if P did not consume input are you going to try Q if it fails. And I think the logic is something about keeping backtracking sensible or error message sensibility. So we actually need to do some checks. So we start off by saying, check how much input you consumed at this point, and keep track of it. And when we reach the jump good instruction, which properly realizes the OR, we say, well, if we failed in P and the input offsets are different, we're just going to say this is a failure, and I'll go to wherever that failure should go next. Otherwise, it will jump over if it succeeded, or if you didn't consume the input and failed, it will fall through to the queue. And attempt allows us to actually perform this backtracking. It says that if you do P and fail, I'll treat it as if you never consumed input. So it will reverse all the input state back to how it was. As well, we actually need some way of reading inputs. They're really simple. Char A will read a character A, and that's represented by a character instruction. And satisfy will read any character that satisfies some predicate. This operator, which I haven't got a name for, I can't pronounce it, but it essentially says, I don't care what P returns, I want to replace it with something else. And it can either choose to do this by mapping const X, or by saying, forget about P and put pure X on. And as long as you're using this top in your code, the compiler will pick whichever one is more suitable. Sometimes they're a bit faster, and the compiler can work out when that should be done. Finally, there's the lift combinators, which essentially take some function and apply it to the results of two parsers. And there are some helpful things that are defined with them. I've mentioned this operator here. This shows explicitly how it works. It takes in the X from PX and the F from PF and returns their application. So let's go back to the grammar that we started with, and let's have a look at identifiers. So I'll highlight the two key parts of this. So some letter are these four instructions, 5 instructions, and some is defined as consing on a P in front of a many P. And we can see that here, so there are two P's, and here's the actual many, which says check the input, try reading a letter, and then many will do a lot like what the OR does. And lift says combine these results at the end. And finally, we do two maps, so there are two perform instructions in there as well, that turn it into a string and apply these to it. The atom makes use of ORs, so we can see this pattern of input checks and jump goods pairing up. And we can also see we read a character, we pop it off, and we call an expression followed by reading a character and popping it off. And what call means is the compiler has worked out that somewhere inside an expression there's a recursion point, i.e. atom is defined in terms of expressions and expressions are determined in terms of atoms. So the compiler has a policy of really aggressive inlining, and obviously you don't want to inline something that's recursive, so it inserts calls every point it finds, and that will basically do a function call. Finally, explorers again have this pattern of ORs. They'll push things on depending on what case. So if we don't read a plus, we just do nothing to the result of the factor. And again, we have this recursive call to expr here. And that's where this part fits in that. So here's everything put together. This is quite a small example, but it already generates quite a lot of instructions. So to make them clear, there's where our identifier is, there's where our numbers are. This is everything that encapsulates an atom, a factor, and the expression is basically everything. So, I haven't spoken yet about what the machine actually is. So we have these 5 stacks. X, which is the operational stack, H, which is handler, etc. And they all do very specific jobs, and they come together to realize these behaviors. So when we want to map something over something, so we're trying to add the results of X and Y, we need a place to store those intermediate results. So that's where the operational stack comes in. The handler stack deals with control flow. You can think of it like an exceptions mechanism. It keeps track of where we go to if we fail. And the input check stack also ensures that if we did consume input, then the semantics should change. For instance, it should not be valid to read a bracket and then fail reading a nested, but because we've read a bracket, happily continue on and say this passed fine. It should fail properly. The call stack is used for when there is recursion. We need to keep track of where we are in the code at the call point and where we should go back to afterwards. And the state stack is only used when we're trying to roll back some state in the machine. It needs to keep track of what the state was before everything went wrong and restore it afterwards. So I'm going to take us through an example quickly, and I don't expect you to understand everything that goes on, but it's just to show a little bit of how these things are actually related to each other. So we're going to start midway through a pass. The character we're looking at is that X up there, and we're going to start reading a factor. And the first thing we're going to do is we're going to read an atom, which is going to give us that X. And from this point, we're going to say, I'm entering some OR, so I need to make sure that the state of the machine is there are 3 input characters read, and if everything fails, I want to go to line 28. And now we try and read a star, which succeeded, and we'll pop it straight off the stack. As a result, we'll push the multiplication instruction on, which implies we're about to do some sort of factor multiplication. And we'll call factor again. Note that 27 is the next line, so 27 has been pushed onto this call stack, and we'll go back to the top. Reading of that atom is going to give us what's in the brackets, because atoms handle brackets. And again, we're going to register that there's this new handler to be pushed, and we should be thinking about all 8 characters having been consumed. We try reading multiply again, and we're going to fail. That takes us down to where that handler told us to go, and jump code says there was a failure, so I'll fall through, and we'll push the identity function onto the stack. From there, we'll take the identity function and that top atom on the stack and do nothing to it. As we reach the end, we're going to return, and that's line 27. And the application will combine those 2 things on the top of the stack into a partial function. As we succeeded quite happily, we didn't fail, jump code is going to take us straight to line 30, and that combines everything, which gives us x times v sub y plus 3, which is what we should have gotten. And this is partway through, so it will now go out and collapse things further. So I've shown the machine, I've shown there's some instructions. How do I know that they will work? Well, there are some laws that hold true for Parsec. There are some more specific to Parsec, but these are the general ones that maintain that things are sensible in some way. That the actions of mapping things and applying things are all working sensibly. The alternative, for instance, states that you can associate alternative operators without any worries. And these are those 4 laws, they all are. These are the ones that we focus on. And we know that Parsley adheres to these laws because we've given it a concrete semantics to every instruction. And every instruction has a well-defined semantics. The rules look like this. And using those, we can actually prove the laws. We start with our 2 sides of the equals, we compile them, and we step through and check that the states as stacks are equivalent on both sides. This is an example of a proof. You can see it in the paper. So once we've got this is all correct, these laws actually give us another byproduct, which is we can actually do optimization with them. So let's go back to this first, the big picture of the grammar, and you'll see that I purposefully wrote two maps next to each other. Now, one of the functor laws says the following: two maps after each other corresponds to the same map with the functions composed. So the compiler is just going to insert that right in. I've removed the and then for brevity, but it is there. And that's great. This is one instruction instead of two. Here we can see this structure here, and we'll actually find that it compiles to this on this side instead of the naive compilation that would be this. And so it actually relates to something else. And I think we should see how it got there. These are the steps it took. In line to that definition of the operator I can't pronounce, and it picks the then pure version. And then it can use a bunch of laws to say, actually, this can be reassociated, that's completely fine. And from there, it can note that that is exactly what map is defined as. So we'll substitute map back in, and we get the more optimized version. So, in summary, we start with this grammar, and we translate it to Parser combinators. Instead of running it using CPS or running it directly, we're going to take that and have a compiler run over it and convert it to this bytecode, not bytecode, instructions. And we can be sure that it's correct from Parsec semantics because we've given these semantics, we've taken the laws and we've proved that they will hold true. And those same laws give us access to some optimizations. There are other optimizations. I mentioned earlier that the compiler can pick between two representations of the same thing. That's a slightly different optimization that doesn't directly relate to these laws. And so that's all I have. Are there any questions?
How did you fit these specific instructions? Did you look at other ones as well?
I'll admit that it was mostly my intuition. So I started off by thinking about how traditional Parser combinator libraries don't match directly to machines that we're running on, especially the JVM. CPS, I tried it, it worked really, really badly. So I said, why are we working in this functional domain when we could be working in an imperative domain and shield ourselves from it? And that's precisely what we do. These instructions execute in a very imperative manner. There are a lot of imperative idioms inside them. But we don't see any of that. We see the functional exterior that's all nice and fluffy. I think that's that.
So you have a proof of the laws that allow you to rewrite the Parser combinator-ish thing into other Parser combinator-ish thing.
Yeah.
You also have a proof that your translation from the Parser combinators things to the instruction set is correct.
Not directly, but you can infer it by saying, I'll compile this and then show that these laws hold true. And to me, at least, that's enough guarantee that those things properly matched up. It doesn't so matter much that the instruction sequences do things on their own. It matters that if I take a combinator, turn it into its instructions, then those things hold true. But I haven't formally proved that the compiler generates the correct code, but it's quite simplistic anyway in its code generation.
It is reasonably simplistic.
So I have a question as well. So, like, how do you practically do the compilation? Like, do you, what's the nuts and bolts here?
Okay, so this is quite interesting. It starts by basically modeling these operators as methods on an implicit class for the purpose of making everything lazy, including the left-hand side of the operators. And from there, it's created this lovely lazy tree. And it will start traversing it, keeping track of what object IDs it's seen. That's how it finds whether there's a recursion point. Once all the recursion points have been found and removed, or turned into a specific fixed node, then it will turn everything into a strict form for efficiency, and will then just traverse through pattern matching to find patterns of AST nodes that it can optimize. In the end, when it does code generation, it will also check for more specific stuff like peak hole optimizations that it can do. And once we're there, those instructions can just be pulled out of the parsers, and they're only computed once.
And then the instructions are interpreted.
The instructions are then interpreted, yeah.
Any other questions? Yes.
So, did you compare the performance with the many other Parsley Combinator libraries of Scala than the official ones?
Yeah, so I've compared against quite a few. I think the fastest I could find in the wild was FastPass, and I haven't had an example where FastPass has beaten me yet. We get close to each other, but I always pull slightly in front. I think the trade-off is whether you find this traditional approach to be nicer or FastPass's sort of magical approach. It sort of works out what you want for you. Personally, I think I prefer the approach I can reason about. So yeah, as far as I'm concerned, FastPass is the fastest, and I'm slightly faster.
You should compare that online and then how you optimize FastPass to make it better.
So I've thought about this. I think if you sort of combine our approaches, you might be able to get faster.
Faster pass.
Yeah, faster pass. So one thing FastPass doesn't do is it doesn't optimize, and quite a lot of the time goes into compiling. Especially if the compiler has to be CPS'd, because I can't allow this to Stack Overflow. So no matter how big these parsers get, I won't Stack Overflow, but that comes at a cost, because I have to trampoline the entire internals. I don't think FastPass does that. But then FastPass might sometimes Stack Overflow if you're not careful. Yep.
So you use these, like the fit laws and so on, to optimize the optimizations. Do they always produce less instructions on your stack machine? Or how do you know that actually optimizations for the stack machine?
So I've only ever encoded ways that make it smaller. There are bigger steps. So if there are multiple steps required to get to an optimization, I will encode that directly. I never allow it to expand to be something bigger than it was before. So it might miss out on some really complicated optimizations it could be doing, but it'll always go down in a sense.
And by go down, you mean the number of instructions?
Yeah, the number of instructions will always decrease, unless unless there happens to be a more optimal sequence of instructions.
So you have a cost model as well for instructions?
Yeah, but that's mostly my intuition. I know which ones are faster than which.
All right, so we're out of time. So let's thank the speaker again.